The test pilot pushed the throttle forward and felt the Pratt & Whitney R2800 double wasp roar to life beneath him. It was March 26, 1942, and Lowry Field near Denver, Colorado, stretched out below as the massive fighter clawed for altitude. The aircraft was designated XP-47B, Experimental Prototype 47 Bomber Escort, and everything about it was wrong by the standards of fighter design that had governed military aviation for 2 decades. It was enormous. The fuselage measured 36 feet 1 inch from spinner to tail. The wingspan stretched 40 feet 9 inches. Empty, the aircraft weighed 9,900 pounds. Fully loaded with fuel and ammunition, it exceeded 13,000 pounds. For comparison, the North American P-51 Mustang, which would become famous later in the war, weighed 7,000 pounds empty. The British Supermarine Spitfire, perhaps the most celebrated fighter of the era, weighed just over 5,000 pounds empty. The XP-47 was a monster, and Republic Aviation's chief engineer, Alexander Kartveli, knew that every pound of that weight served a purpose. Buried in the rear fuselage, connected to the engine by a complex system of ducting that ran along both sides of the cockpit and underneath the pilot's seat, was a General Electric Type B turbosupercharger. This single component, roughly the size of a beer keg, was the reason the aircraft existed at all. As the test pilot climbed through 15,000 feet, he reached down and adjusted the turbo control. The system responded smoothly. Exhaust gases from the 18-cylinder radial engine, travelling at over 1,000 degrees Fahrenheit, spun the turbine wheel at speeds exceeding 20,000 revolutions per minute. The turbine drove a compressor that forced additional air into the engine's cylinders, compensating for the thin atmosphere at altitude. At 20,000 feet, where other fighters began to lose power and maneuverability, the P-47 was just beginning to perform. At 25,000 feet, it was still climbing strongly. At 30,000 feet, altitudes where bomber crews wore heated suits and oxygen masks to survive, the Thunderbolt's engine continued to produce power that would have been impossible without forced induction. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The pilot leveled off at 35,000 feet and checked his instruments. Oil pressure steady, cylinder head temperatures within limits, manifold pressure holding at 52 inches of mercury, an impossible number for a naturally aspirated engine at this altitude. The turbosupercharger was working exactly as the engineers had promised, but the real test was still ahead. Republic Aviation had bet everything on this design. The Army Air Corps had ordered the aircraft based on performance specifications that seemed fantastical. Cruise at 300 miles per hour at 25,000 feet, fight effectively at 35,000 feet, climb to 15,000 feet in under 5 minutes, survive combat damage that would destroy lighter fighters, carry enough fuel to escort bombers deep into enemy territory. Every one of these requirements demanded an aircraft larger and heavier than conventional fighter doctrine allowed, and every one of them depended absolutely on the turbosupercharger, functioning reliably in combat conditions that would test it to destruction. The pilot pushed the stick forward and dove toward the thin clouds below, building speed, feeling the airframe shudder slightly as it approached 400 miles per hour. At this speed, at this altitude, the XP-47 was faster than anything the Luftwaffe could put in the air. The question that would determine whether Republic Aviation survived as a company, whether thousands of pilots lived or died, whether the strategic bombing campaign against Germany succeeded or failed, was simple. Could this massive, complex, over-engineered turbo-supercharger system work reliably enough to matter in actual combat? The answer to that question began not in Colorado in 1942, but in a General Electric laboratory in Massachusetts 25 years earlier, with an engineer who believed that exhaust gases were being wasted. Sanford Alexander Moss had joined General Electric's steam turbine division in 1903, bringing with him a doctorate from Cornell University and an obsession with thermodynamics. He understood that internal combustion engines, whether in automobiles or aircraft, were profoundly inefficient machines. They converted only about 30% of the fuel's energy into useful work. The remaining 70% was lost as heat through the exhaust system and cooling apparatus. Moss believed this waste could be captured and used. In 1918, while working at GE's Lynn, Massachusetts facility, he began experimenting with exhaust-driven turbines. The concept was straightforward in theory, but murderously difficult in practice. Hot exhaust gases leaving an engine carried tremendous energy. If those gases could be channeled through a turbine wheel, they could drive a compressor that would force additional air into the engine, increasing power output at altitude where air density decreased. The challenges were immediate and severe. Exhaust gases from piston engines were not steady streams, but violent pulses corresponding to the firing sequence of the cylinders. These pulses created vibration and uneven forces on the turbine wheel. The temperatures involved, often exceeding 1,200 degrees Fahrenheit, exceeded the heat tolerance of most metals available at the time. The turbine had to spin at extraordinary speeds, often above 20,000 revolutions per minute, creating centrifugal forces that threatened to tear the wheel apart. The compressor side presented different but equally difficult problems. Compressing air generates heat through the laws of thermodynamics. The compressed air entering the engine cylinders had to be cool enough not to cause pre-ignition or detonation, yet hot enough to mix properly with fuel. The compressor wheel had to match its speed precisely to the turbine's rotation, while handling vastly different volumes and pressures of air compared to exhaust gases. Moss spent years refining the design. He experimented with different turbine wheel configurations, testing various blade angles and materials. He developed intercooler systems to reduce the temperature of compressed air before it entered the engine. He created wastegate valves that could bypass excess exhaust gases around the turbine when maximum boost wasn't needed, preventing overpressurization that could destroy the engine. By 1923, Moss had produced a functioning turbosupercharger that demonstrated the concept's viability. The Army Air Service, intrigued by the possibility of maintaining engine power at high altitudes, funded further development. Moss and his team at General Electric conducted tests at Pikes Peak in Colorado, where the 14,000-foot elevation provided a natural laboratory for studying high-altitude engine performance. The results were remarkable. An aircraft engine that produced 400 horsepower at sea level might produce only 200 horsepower at 15,000 feet without supercharging. With Moss's Turbosupercharger, the same engine could maintain close to its sea-level power output at 20,000 feet or higher. The implications for military aviation were profound, particularly for bomber aircraft that needed to operate above the effective ceiling of anti-aircraft artillery and enemy fighters. But the technology remained experimental throughout the 1920s and 30s. The turbosuperchargers were heavy, complex, and temperamental. They required constant maintenance and adjustment. The ducting systems needed to route exhaust gases to the turbine and compressed air back to the engine, added weight and complexity to aircraft design. Most importantly, the benefits of high-altitude performance didn't justify the costs for the type of warfare military planners envisioned during the interwar years. Fighter doctrine in the 1930s emphasized maneuverability and rate of climb at low to medium altitudes. Dogfights were expected to occur between 10,000 and 20,000 feet, where naturally aspirated engines performed adequately. The additional weight and complexity of turbosuperchargers seemed unnecessary for fighters. They were reserved primarily for high-altitude bombers and reconnaissance aircraft, where the ability to operate above 30,000 feet provided clear advantages. Alexander Kartveli understood that this conventional wisdom was about to become obsolete. Born in Tiflis, Georgia, in 1896, Kartveli had studied aviation in Paris before immigrating to the United States in 1927. He joined the Seversky Aircraft Company, which would later become Republic Aviation, and by 1939 he was chief engineer responsible for the company's fighter designs. Kartveli had been following developments in Europe with growing concern. The Battle of Britain, fought primarily in the summer of 1940, had demonstrated several emerging realities about modern air warfare. First, combat was occurring at increasingly higher altitudes, as both attackers and defenders sought altitude advantage. Second, heavily armed and armoured aircraft could survive combat damage that would have destroyed earlier, lighter fighters. Third, long-range escort capability was becoming essential as strategic bombing campaigns required fighters to accompany bombers deep into enemy territory. In September 1940, the Army Air Corps issued a specification for a new fighter aircraft. The requirements seemed almost contradictory. The aircraft needed to carry at least 6 50-caliber machine guns with substantial ammunition loads. It needed armor protection for the pilot and critical systems. It needed self-sealing fuel tanks that could survive hits from enemy fire without catastrophic fuel loss. It needed sufficient range to escort bombers on missions lasting 3 to 4 hours. And it needed to maintain high performance at altitudes above 30,000 feet. Kartveli began his design work with a fundamental decision that would determine everything that followed. He chose the Pratt & Whitney R2800 Double Wasp as the power plant. This was an 18-cylinder, 2-row radial engine that produced 2,000 horsepower at sea level. It was the most powerful production aircraft engine available in the United States at that time, but it was also massive, weighing over 2,000 pounds. The R2800's power output made it ideal for a heavily armed, heavily armoured fighter, but its performance degraded rapidly at altitude without supercharging. Pratt & Whitney offered mechanically driven superchargers that attached directly to the engine, but these consumed significant power to operate and had limitations in their altitude capability. Kartveli chose instead to design around a turbosupercharger system, accepting all the weight and complexity that decision entailed. The turbosupercharger installation became the defining feature of the P-47's design. The turbo unit itself weighed approximately 150 pounds. The ducting system required to route exhaust gases from the engine to the turbo, and then route compressed air back to the engine, added hundreds of additional pounds. The exhaust ducts ran along both sides of the fuselage underneath the cockpit, each constructed from heavy steel capable of withstanding exhaust temperatures, exceeding 1,000 degrees Fahrenheit. The intake ducting that brought compressed air from the turbo back to the engine was equally complex. This air, heated by compression to temperatures that could damage the engine, had to pass through an intercooler to reduce its temperature before entering the carburetor. The intercooler added more weight and required its own ducting for cooling airflow. The entire system, from engine exhaust to turbine to compressor to intercooler to engine intake, formed a continuous loop that wrapped around and through the aircraft's fuselage. This installation drove almost every other design decision. The fuselage had to be large enough to accommodate the ducting, pushing the overall dimensions far beyond normal fighter proportions. The cockpit sat high on the fuselage, giving the pilot excellent visibility, but also creating a characteristic humpbacked appearance that would become the Thunderbolt's visual signature. The landing gear, needing to be long, enough to provide ground clearance for the massive propeller required by the powerful engine, retracted inward toward the fuselage centerline rather than outward into the wings. Republic Aviation completed the first XP-47B prototype in May 1941. The aircraft represented an investment of hundreds of thousands of dollars and countless engineering hours. When company test pilot Lowry Brabham first climbed into the cockpit, he found himself sitting in what appeared to be a flying oil barrel. The fuselage diameter measured 4 feet 8 inches at its widest point, enormous by fighter standards. The canopy sat so high that ground crew needed a ladder to help pilots board the aircraft. The first test flight revealed problems immediately. The turbosupercharger installation generated heat that radiated through the fuselage structure. Temperatures in the cockpit climbed rapidly, making extended flight uncomfortable and potentially dangerous. The exhaust ducting, running beneath the pilot's seat and along the fuselage sides, turned the cockpit into an oven. Engineers installed additional insulation, but this added weight to an aircraft already straining against its design limits. The ducting itself presented constant challenges. The exhaust passages had to withstand temperatures exceeding 1,000 degrees while remaining airtight under pressure. Any leak allowed superheated exhaust gases to escape into the fuselage, creating fire hazards and reducing turbo efficiency. The joints where duct sections connected were particularly vulnerable. Republic's engineers experimented with various gasket materials and clamp designs, seeking combinations that could maintain seals under thermal cycling that expanded and contracted the metal dozens of times during each flight. The intercooler system proved equally problematic. Compressed air leaving the turbo's compressor stage reached temperatures approaching 400 degrees Fahrenheit. This air had to be cooled to approximately 150 degrees before entering the engine, or it would cause detonation that could destroy pistons and cylinder heads. The intercooler core, positioned in the lower fuselage, used ram air drawn through intake scoops to cool the compressed charge air passing through its internal passages. But the intercooler's position created aerodynamic complications. The air scoops produced drag that reduced the aircraft's maximum speed. Engineers worked to optimize the scoop design, balancing cooling efficiency against drag penalties. They tested dozens of configurations in Republic's wind tunnel, measuring pressure drops and cooling performance. Each design iteration required new tooling and fabrication, consuming time and resources that Republic could barely afford. The Turbosupercharger's control system added another layer of complexity. The turbo had to respond to changing flight conditions and pilot demands while maintaining proper boost pressure without overstressing. The engine. A mechanical linkage connected the throttle to a wastegate valve that bypassed excess exhaust gas around the turbine. Opening the wastegate reduced turbo speed and boost pressure. Closing it increased both. The system had to react smoothly across the aircraft's entire operating envelope, from sea level to 40,000 feet, from idle power to maximum combat power. Test pilots reported that the turbo control required constant attention and adjustment. Unlike mechanically driven superchargers that responded instantly to throttle changes, the exhaust-driven turbo had inherent lag. When the pilot advanced the throttle, requesting more power, several seconds passed before the increased exhaust flow spun the turbine faster and raised boost pressure. This lag made precise power management difficult, particularly during combat maneuvers that required rapid throttle movements. Republic's engineers worked to refine the control system throughout late 1941 and early 1942. They adjusted wastegate linkages, modified spring tensions, and calibrated the relationship between throttle position and turbo output. Test pilot after test pilot climbed to altitude and experimented with different power settings, recording boost pressures, manifold temperatures, and engine responses. Gradually, through hundreds of test flights and thousands of adjustments, the system became more predictable and controllable. But predictability in test conditions didn't guarantee reliability in combat. The Army Air Forces had ordered the P-47 into production based on prototype performance, but actual combat experience would be the final test. In late 1942, the first production P-47 seconds began reaching operational units. The 56th Fighter Group, based at Bridgeport, Connecticut, received Thunderbolts in June. The 78th Fighter Group converted to P-47 seconds in November. Both units began training for deployment to England, where they would join the 8th Air Force's strategic bombing campaign against Germany. The transition to the new aircraft challenged even experienced pilots. The P-47 flew differently than anything they had flown before. It was heavy and built up speed in dives that could exceed 500 miles per hour, approaching the aircraft's structural limits and entering compressibility regimes where control surfaces lost effectiveness. It climbed slowly at low altitudes compared to lighter fighters like the P-51 or the British Spitfire. But above 20,000 feet, where the turbo's contribution became decisive, the Thunderbolt's performance transformed completely. The 56th Fighter Group arrived in England in January 1943 and began operations from King's Cliff Airfield in Northamptonshire. Lieutenant Colonel Hubert Zemke commanded the group, bringing experience from earlier combat in P-40 Warhawks. Zemke understood that his pilots needed to learn the Thunderbolt's capabilities and limitations quickly, before those lessons were taught by the Luftwaffe at lethal cost. The group's first escort mission occurred on April 8, 1943. 48 P-47 seconds took off to accompany B-17, flying fortresses bombing targets in Belgium and France. The mission profile required the fighters to climb to 25,000 feet, rendezvous with the bombers, and maintain formation while scanning for German interceptors. The turbosuperchargers performed exactly as designed, allowing the heavily loaded fighters to reach altitude with power to spare. But the mission also revealed critical limitations. The P-47's combat radius, the distance it could fly from base while retaining fuel for combat and return, was approximately 175 miles. This was insufficient to escort bombers attacking targets deep in Germany. The fortresses would fly beyond escort range and face German fighters alone for portions of their mission. Until Republic could develop conformal fuel tanks to extend the Thunderbolt's range, escort coverage would remain limited. The Luftwaffe's response to American daylight bombing had been evolving throughout 1942 and early 1943. German fighter units had learned that attacking bombers from the rear, where defensive fire was lighter, produced better results than frontal attacks. They had also discovered that American escort fighters had limited endurance and could be avoided by waiting until the escorts turned back before launching attacks. On April 15, 1943, the limitations of early escort tactics became painfully clear. B-17 seconds attacking Bremen flew beyond P-47 escort range. German fighters waited until the Thunderbolts turned for home, then swarmed the bomber formations. 16 bombers were shot down. The losses demonstrated that strategic bombing without continuous fighter escort was unsustainable. Republic Aviation's engineers accelerated development of drop tanks, external fuel, containers that could be jettisoned when empty or when combat required maximum performance. The first successful drop tank design added 75 gallons of fuel capacity, increasing combat radius to approximately 230 miles. Later designs would carry up to 150 gallons, pushing combat radius past 300 miles and allowing P-47 seconds to escort bombers to targets throughout Western Germany. But the drop tanks created new challenges for the turbosupercharger system. The additional weight altered the aircraft's center of gravity and required careful fuel management to maintain proper balance throughout the flight. The external tanks also increased drag, reducing speed and climb performance until they were dropped. Pilots had to learn when to retain the tanks for maximum range and when to jettison them for combat maneuverability. The altitude performance that the turbosupercharger provided became increasingly valuable as combat experience accumulated. German fighters, primarily Messerschmitt Bf 109s and Focke-Wulf W190, as typically engaged bomber formations between 20,000 and 25,000 feet. The P-47 seconds, operating at 28 to 30,000 feet, could dive on German fighters with significant energy advantage. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Lieutenant Robert Johnson of the 56th Fighter Group described his first high-altitude engagement in June 1943. His flight was cruising at 28,000 feet when they spotted German fighters below attacking a bomber formation. Johnson pushed the nose down and applied full throttle. The Thunderbolt accelerated rapidly, building speed throughout the dive. By the time he reached the German formation's altitude, his airspeed indicator showed over 450 miles per hour. The energy advantage was decisive. Johnson fired a burst into a Focke-Wulf 190 that never saw him coming. The German fighter disintegrated under the concentrated fire from 850 caliber machine guns. Johnson pulled up sharply, using his excess speed to climb back above the fight, ready to dive again. The tactic, called boom and zoom, exploited the P-47's strengths while avoiding prolonged turning fights where lighter German fighters held advantages. The turbosupercharger's reliability in combat conditions exceeded expectations. Unlike mechanically driven superchargers that could fail if pushed beyond design limits, the exhaust-driven turbo had no direct mechanical connection to the engine. If the turbo failed, the engine continued running, though with severely reduced power at altitude. Pilots could still fly home on turbo failure, descending to lower altitudes where the engine produced adequate power without supercharging. The mission that demonstrated the P-47's unique capabilities occurred on August 17, 1943, during raids against ball-bearing factories in Schweinfurt and Messerschmitt production facilities in Regensburg. The 8th Air Force launched 376 heavy bombers on these deep penetration raids, stretching American air power to its limits. P-47 groups provided escort for the initial portions of the mission, but the targets lay beyond even extended escort range. The 56th Fighter Group escorted bombers to the limit of their fuel range, then turned for home as briefed. But Colonel Zemke, monitoring radio traffic, heard increasingly desperate calls from bomber crews under heavy attack. He made a decision that violated standing orders, but demonstrated the kind of tactical flexibility that saved lives throughout the war. He ordered his group to extend their escort time by 5 additional minutes, burning into fuel reserves normally held for emergencies. Those 5 minutes allowed the Thunderbolts to engage German fighters that had assumed the escorts had already departed. The 56th claimed 13 German aircraft destroyed for the loss of 3 P-47 seconds. More importantly, the extended escort disrupted German attack coordination during the crucial minutes when bomber formations were most vulnerable. The engagement occurred at altitudes between 28,000 and 32,000 feet. At these heights, the Turbosupercharger's contribution was absolute. German fighters struggled to maintain performance. Their engines, equipped with single-stage mechanically driven superchargers, lost power rapidly above 25,000 feet. The Messerschmitt 109G model, the primary German fighter at this point in the war, was rated to operate effectively up to about 38,000 feet maximum ceiling, but its combat performance degraded significantly above 28,000 feet. The Focke-Wulf 190A, powered by a BMW radial engine, had even more pronounced altitude limitations. Its combat ceiling was approximately 34,000 feet, but effective fighting performance ended around 25,000 feet. Above that altitude, the 190's rate of climb decreased to the point where pursuing climbing American aircraft became impractical. The P-47, by contrast, maintained strong performance through 35,000 feet and could operate, though with reduced effectiveness, above 40,000 feet. Test flights had pushed stripped Thunderbolts to altitudes exceeding 42,000 feet, though such heights were impractical for combat operations that required oxygen reserves and fighting capability. The psychological impact on German fighter pilots was significant. They had grown accustomed to altitude advantage over earlier American escort fighters. The P-47's arrival changed that calculation. Captain Heinz Nock, a Luftwaffe fighter ace who recorded his experiences in a diary later published as I Flew for the Führer, described his first encounter with Thunderbolts in July 1943. He noted with surprise that the American fighters were operating several thousand feet above his formation and dove on them with tremendous speed advantage. German pilots quickly learned to respect the Thunderbolts' high-altitude performance and diving speed. They developed tactics to counter these advantages, primarily by forcing American fighters into turning engagements at medium altitudes, where German fighters' lower wing loading and lighter weight provided maneuverability advantages. But these counter-tactics only worked when the P-47 pilots accepted the engagement terms. Disciplined Thunderbolt pilots maintained altitude and speed advantage, engaging only when conditions favored them. The Turbosupercharger required careful maintenance to sustain this performance. Ground crews at forward bases in England learned to inspect the ducting systems thoroughly between missions. They checked exhaust pipes, cracks that could develop from thermal stress. They examined gaskets and seals for deterioration. They tested wastegate operation to ensure proper control response. They cleaned intercooler cores that could become fouled with oil residue or debris. Republic Aviation established maintenance procedures based on combat experience feedback. Critical inspections occurred every 25 flight hours. Complete turbo system overhauls happened every 100 hours. The maintenance requirements were demanding, but they were manageable with proper training and parts supply. The Turbosupercharger proved to be robust enough for sustained combat operations when properly maintained. The P-47's success in combat drove unprecedented production expansion. Republic Aviation's Farmingdale, New York facility, which had employed approximately 5,000 workers in 1941, expanded to over 25,000 employees by 1943. The factory operated 3 shifts, 24 hours per day, 7 days per week. Production rates climbed from 30 aircraft per month in early 1942 to over 300 per month by mid-1943, but turbosupercharger production became the constraining factor. General Electric's supercharger division in Lynn, Massachusetts, could not produce turbo units fast enough to match airframe production rates. The company invested in new manufacturing equipment and expanded floor space, but turbo production required specialized skills and precision manufacturing that couldn't be ramped up as quickly as airframe assembly. Each turbosupercharger contained components that had to be manufactured to tolerances measured in thousandths of an inch. The turbine wheel, spinning at over 20,000 revolutions per minute while exposed to 1,000-degree exhaust gases, required precise balancing and heat-resistant alloys. The compressor wheel demanded equally precise manufacturing to achieve efficient air compression without excessive power consumption. The bearing systems supporting both wheels had to operate reliably under extreme temperatures and centrifugal forces. General Electric established quality control procedures that tested every turbosupercharger on dynamometer stands before shipment. These tests measured boost pressure output across the operating range, checked for exhaust leaks, verified wastegate operation, and confirmed bearing lubrication systems functioned properly. Units that failed any test were torn down, inspected, and rebuilt. The rejection rate during early production ran as high as 15%, but improved to below 5% as manufacturing processes matured. The turbosupercharger's complexity created maintenance challenges in operational theatres. Fighter groups in England, North Africa, Italy, and later France required trained technicians who understood the system's operation and could diagnose problems accurately. The Army Air Forces established specialized training programs at technical schools in the United States. Mechanics learned to recognize symptoms of turbo malfunction, perform field repairs, and determine when complete unit replacement was necessary. Combat damage presented unique challenges. The turbo's location in the rear fuselage made it vulnerable to enemy fire approaching from behind, the classic fighter attack position. Damage to the turbine wheel from shell fragments could cause catastrophic failure at high rotational speeds. Damage to ducting systems could create exhaust leaks that reduced performance and created fire hazards. Maintenance crews became expert at assessing battle damage and determining whether aircraft could be repaired at forward bases or required return to depot facilities. Republic Aviation continued refining the turbosupercharger installation throughout the war. The P-47D model, which entered service in early 1944, incorporated improvements based on combat experience. The intercooler received better cooling airflow through redesigned intake scoops. The turbo control system gained an automatic regulator that reduced pilot workload by maintaining preset boost pressures. The ducting system received reinforcement in areas where cracks had developed in earlier models. The most significant P-47 variant, the D-25 and later production blocks, featured a bubble canopy that replaced the original Razorback design. This change improved pilot visibility dramatically, but also required relocating some internal components to maintain proper center of gravity. The turbosupercharger installation remained essentially unchanged, testimony to the original design's soundness. By late 1944, P-47 production reached its peak, with over 700 aircraft delivered per month from Republic's Farmingdale facility, and a second production line established in Evansville, Indiana. Curtiss-Wright Corporation also produced P-47 seconds under license at their Buffalo, New York plant, adding several thousand more aircraft to the total. The combined production from all sources exceeded 1,000 aircraft per month during the war's final year. The turbosupercharger proved reliable enough that pilots trusted the system completely. This trust allowed tactical innovations that exploited the P-47's unique capabilities. Fighter groups developed high-altitude patrol tactics that positioned Thunderbolts above bomber formations at 30 to 32,000 feet, ready to dive on any German fighters attempting attacks. The altitude advantage, made possible by the turbosupercharger, became standard doctrine for P-47 operations throughout the European theatre. The Turbosupercharger's contribution to the P-47's combat effectiveness went beyond simple altitude performance numbers. It enabled a fighting style that fundamentally altered the dynamics of air combat over Europe. To understand why, one must examine the physics of energy management in fighter combat, concepts that became known as energy maneuverability theory in later decades, but were understood intuitively by experienced pilots during World War II. An aircraft in flight possesses two forms of energy: kinetic energy from its velocity and potential energy from its altitude. Skilled fighter pilots learned to trade one form for the other, converting altitude into speed during dives and converting speed back into altitude during climbs. The aircraft that could maintain higher total energy and convert between energy states more efficiently held a decisive advantage in combat. The P-47's Turbosupercharger allowed it to operate at higher altitudes than most opposing fighters, while maintaining significant power output. This altitude represented potential energy that could be converted into kinetic energy, into speed, at the pilot's discretion. A Thunderbolt cruising at 30,000 feet could dive to 20,000 feet and reach speeds approaching 500 miles per hour. At such speeds, the aircraft possessed enormous kinetic energy that could be used for rapid climbs back to altitude, for high-speed escapes, or for devastating attacks on slower opponents. German fighters attempting to intercept B-17 and B-24 bomber formations operated under severe energy constraints. They needed to climb to bomber altitude, typically 25,000 feet, while carrying heavy armament and sometimes external rockets for attacking the bombers. This climb consumed fuel and time. Once at bomber altitude, they had limited endurance for combat before fuel constraints forced them to disengage and return to base. The P-47 seconds, positioned several thousand feet above the bombers and the German fighters attacking them, entered combat with both altitude and speed advantage. They dove from above, accelerating to speeds the German fighters couldn't match. They attacked, broke away using their excess speed to zoom, climb back to altitude, and repositioned for another attack. If German fighters attempted to pursue them in the climb, the Thunderbolt's superior high-altitude performance allowed them to pull away. If German fighters attempted to escape by diving, the P-47's excellent dive performance and structural strength allowed pursuit to lower altitudes. This tactical approach, refined through hundreds of combat missions during 1943 and 1944, proved devastatingly effective. It also proved nearly impossible to counter without the German aircraft industry producing fighters with equivalent high-altitude performance. Germany did develop such aircraft, most notably the Fokker-Wulftar 152 and certain high-altitude variants of the Messerschmitt 109, but these appeared too late and in too few numbers to affect the strategic situation. The psychological dimension of the P-47's altitude advantage extended beyond individual combat encounters. German fighter pilots, knowing that American escorts operated above them with energy advantage, had to approach every bomber interception with the knowledge that Thunderbolts might dive on them at any moment. This uncertainty degraded the effectiveness of attacks on bomber formations. Pilots had to divide attention between their primary targets, the bombers, and potential threats from above. Some German units adapted by assigning specific fighters to fly high cover, watching for American escorts, while other fighters attacked bombers. But this division of forces reduced the number of fighters available for bomber attacks and created coordination challenges. The high cover fighters, positioned to counter P-47 seconds, were typically unable to provide direct support to their comrades, attacking below when Thunderbolts dove through the formation. The Turbosupercharger's contribution to this tactical equation was absolute. Without it, the P-47 would have been another medium-altitude fighter competing with German aircraft on roughly equal terms. With it, the Thunderbolt operated in a performance envelope its opponents couldn't reach, dictating engagement terms and imposing energy disadvantages that skilled pilots exploited ruthlessly. Field maintenance crews in England learned to treat the Turbosupercharger system with respect approaching reverence. They knew that every properly functioning turbo meant their pilots had the altitude performance that kept them alive. Maintenance officers established procedures ensuring that no aircraft flew combat missions with questionable turbo operation. If a test flight revealed any anomaly in boost pressure, wastegate control, or intercooler performance, the aircraft was grounded until the problem was resolved. The P-47 Thunderbolt served throughout the remainder of World War II in every theatre where American forces operated. Total production reached 15,686 aircraft by war's end in August 1945, making it the most produced American fighter aircraft in history at that time. Of these, Republic's Farmingdale plant produced 9,087 aircraft. The Evansville plant produced 6,242, and Curtiss Wright's Buffalo facility produced 354, before that production line closed in 1944. The aircraft's combat record reflected its capabilities. P-47 pilots were credited with 3,752 enemy aircraft destroyed in air-to-air combat in the European theatre alone. But the Thunderbolt's impact extended beyond aerial victories. Its rugged construction and powerful engine made it exceptionally effective in ground attack roles. Fighter groups increasingly assigned P-47 seconds to attack German transportation networks, destroying locomotives, trucks, and rail yards that supplied Wehrmacht units fighting on the ground. The Turbosupercharger, designed to enable high-altitude bomber escort, proved equally valuable for ground attack missions that occurred at low altitudes. The system's reliability meant pilots could climb rapidly to medium altitudes for transit to target areas, dive to low level for attacks, then climb back to safer altitudes for the return flight. This operational flexibility, cycling repeatedly between altitude extremes, tested the Turbosupercharger system severely, but the robust design handled the demands. After the war, analysis of the strategic bombing campaign against Germany confirmed what combat crews had understood intuitively. Effective fighter escort was essential for daylight precision bombing to succeed. The period from late 1943 through mid-1944, when P-47 groups provided increasingly effective escort coverage, marked the transition from unsustainable bomber losses to acceptable attrition rates that allowed the campaign to continue. The P-47's specific contribution to this transition was its availability in large numbers and its ability to escort bombers to targets throughout Germany once drop tank range was extended. The P-51 Mustang, which began arriving in significant numbers in early 1944, offered superior range and higher performance at medium altitudes. But the P-47 remained in service throughout the war, equipping 16 fighter groups in the European theatre at war's end. The Turbosupercharger technology that made the P-47's high-altitude performance possible continued development after the war. Jet engines, which began entering service in the final months of World War II, used turbine technology conceptually similar to the exhaust-driven turbos. The principles of compressing intake air to increase power output at altitude transferred directly to turbojet and later turbofan engine designs. But the specific configuration that characterized the P-47, a large piston engine connected to a remote turbosupercharger through ducting systems, represented an evolutionary dead end. Post-war aircraft design moved toward jet propulsion, which integrated compression and combustion into a single system without requiring the complex ducting that had dominated the P-47's internal layout. The men who maintained the P-47's turbosupercharger systems in combat theatres returned home with specialized knowledge that transferred to post-war aviation industry jobs. General Electric, which had developed the turbo technology, became a major manufacturer of jet engines for both military and civilian aircraft. Republic Aviation continued producing military aircraft through the 1960s, though none achieved the success or production numbers of the Thunderbolt. Alexander Kartveli, whose decision to design around the turbosupercharger had made the P-47 possible, continued as Republic's chief engineer. He designed the F-84 Thunderjet and later the F-105 Thunderchief, both successful military aircraft. But he understood that the P-47 represented a unique moment in aviation history when a specific technology, the exhaust-driven Turbosupercharger, enabled capabilities that would soon be achieved through entirely different means. The test pilot who flew that prototype in March 1942, climbing through 35,000 feet and feeling the Turbosupercharger maintain power where other aircraft would have gasped for oxygen-thin air, had witnessed the vindication of engineering decisions that had seemed risky when made. The massive, complex, over-engineered installation that critics had questioned proved to be exactly what was needed. The weight penalty was acceptable. The maintenance demands were manageable. The performance advantage was decisive. In the end, the Turbosupercharger's story within the P-47 program illustrates a fundamental truth about military technology development. Revolutionary capabilities often require accepting complexity and risk during design and development. The engineers at Republic Aviation and General Electric had bet that exhaust-driven supercharging could be made reliable enough for combat operations. They had been right, and thousands of pilots flew home safely because of that engineering decision. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.